So these don't have square roots on them. We're just simplifying the fractions, remembering some of those exponent laws we talked about a couple of days ago. So on this left-hand one, there's a couple of different pathways through it. What do we notice first? How could we simplify this one? Combine what? More specific. More specific, how? Yeah, in the numerator, since we have these two pieces being multiplied together, we can add those exponents together. So I can write this as x to the 4 plus 2 over x cubed, which is the same thing as x to the 6th over x cubed. So when we multiply the bases, we add the exponents. So what else can we do to simplify this? When we divide, what do we do with our exponents? Subtract them. So I can set this up as x to the 6 minus 3, which is the same thing as x cubed. If that does not work for you, you can also think about this as being 6 x's. So x times x times x times x times x times x. 6 of them, right? Over 1, 2, 3 of them. That one cancels out. That one cancels out. That one cancels out. And I have 3 of them that are left over. That's where this 3 comes from. So that's what it's doing. It's canceling them out just without us having to write all of them out. So this fraction simplifies down to be x to the 3rd. Right one is a very similar vibe. We just have 3 different letters. So looking at our x's, we've got x to the 5th over x to the 7th. What are we going to wind up left over when we simplify? Yes, x squared, but in the denominator. I have 5 x's on the top, 7 x's on the bottom. If you do it as subtraction, you get x to the minus 2. When we have a negative exponent, it's down in the bottom. Or if you think of it as the canceling out, I have 2 leftovers down on the bottom. How about for my y's? Y is going to be on the top, and what's our exponent going to be? 2. I have 3 y's on the top, 1 y on the bottom, so one of them cancels out. Yep. And what exponent is going to be on our z on the bottom? Just a 1, so we don't usually write that. So that is old Algebra 1 skills that we just haven't used in a hot minute. Questions on bell work? Okay, because we're going to talk through some properties of our radicals and our radical functions that we have already used, honestly. We just hadn't given them names. And then we're going to practice some more with the simplifying, because I've had a lot of questions come up in the simplifying, especially when things don't come out all tidy with the numbers. So we're going to practice with those today. And then we'll use the properties more tomorrow. I just wanted to really focus on that simplifying part because we got a little bit stuck on that. So we're going to have a little bit of introduction that we're going to use a little bit more tomorrow because I wanted to tie some things together. So we're going to start with our properties. And we've used both of these properties already. The product property and our quotient property. The product property we have used bunches and bunches and bunches of times. Pretty much every time we have solved a radical, we have used our product property. Because what it says is if I have 2 radicals that are multiplied together, I can put them under the same radical and multiply them. We have used this literally every time we have solved or simplified a radical, just going in that direction. We take our one big radical and split it apart. That is using our product property. We just hadn't given it a name. Same thing with our quotient property. We've never written it with the division symbol, like with this, with the fraction that just has dots. But we have written it like this, where I have square root of x over square root of y, which does mean the same thing as the square root of x over y. And again, we have used it this way repeatedly. Every time we have done a radical that had a fraction in it, we've used quotient property. We just hadn't given it a name. And I'm never going to ask you to like cite the name. Like you don't have to write like a proof saying because of the product property, I can do this. But it's good to give us the names on things, and we're going to work more with the properties. Like I said, we're going to hit the properties a lot more tomorrow. I just wanted us to really focus on our simplifying stuff today because I've had a lot of people getting stuck, and I wanted to kind of address that before we get into the next piece of it. So we're going to do ideally 6, but possibly only 4 simplifyings today. Depends on how quickly we get through them. Our first period, we did not get through very many at all. So these two properties, we use bunches and bunches. We have used them repeatedly before, but we just hadn't ever given them names. So, let's see. Looks like we still got 2 people writing, so write it down so I can change the page. Because we're going to start with some familiar simplifying things, and we'll get into some things that have like leftover bits, because those make us unruly. What's up? Yeah? It takes a lot for me to wind up saying no to that, so... Like at this point, y'all are big enough that I'm just like, y'all know consequences for things. Not only the consequences of skipping class. All right. So one place I've had a lot of people get stuck is to know when we're done. So this is kind of a checklist for things, how we know we're done simplifying. So it's rarely going to be a thing that we change our index, but if we can simplify when it's in a fraction form, we can simplify our index. If we have no factors under the radicand, so the number underneath the radical, I don't have anything that's a factor that we could pull out, and that we have no fractions in there. So our exponents need to be smaller than our index, and we don't have fractions under a radical. So we can check our powers, we can check for factors, and we can check our fractions. Those are how we know that we're done. And we'll talk through it as we go through some of these practice ones. But that was another thing that we had that a lot of people were stuck on, is how do we know when to stop? We run out of things to do, mostly. So let's practice this. The left one is very much like things we've done before. It is a square root. I've got square root of 75, x to the 12th, y to the 7th. So this is when we use our product property. This is our square root, so our index is 2. So we don't usually write something there, but we split this up. Our square root of 75, our square root of x to the 12th, and our square root of y to the 7th. So we have done this and split this up into separate pieces for every single radical we've done that had more than one term. That's the product property. That is exactly what we just wrote down. This lets us simplify each of these pieces individually. So when we're looking at our square root of 75, What do we notice? 75 is not a perfect square. Does it have one inside, though? I was going to say, yeah, we can take 75 and break it down to be 25 times 3. We like to break it down into 25 and 3 because 25 is a perfect square. So what is our simplified form, our simplified radical form of square root of 75? Just say, super close. Yes. So our square root of 25, that gives us our 5. Once we've taken the square root of 25, it is no longer in a house. But our 3 does not get to come outside. It's stuck inside. It doesn't have a buddy. Square root of 25, we know. You could also continue to break that down and make it 5 times 5 times 3 and pull that out as a pair. It does the same thing. How about our square root of x to the 12th? What's that going to simplify to be? Correct. So we're making pairs, and I have a pile of 12 things. I can make 6 pairs. How about our y to the 7th? I can make 3 full sets, so we get our y cubed, and I have a leftover y. So I can make 3 full pairs, and I have 1 sock left in the basket. So our last step on this is to put all the things outside the radical together, all the things inside the radical together. So our final answer is going to be our 5x to the 6th y cubed square root of our 3 and y. The way we can tell we're done is inside our radical here, I do not have any powers that are bigger than my index. My index is 2. I do not have any powers bigger than my index, and 3 does not have any perfect square factors. So that's the way we can tell we're done, is when our powers are all smaller than our index inside the radical. So that's our final answer on that one. We've done ones like that one before, but we're just talking through it for a little bit here in advance. Questions on that first one? Just giving us a little barrier here. All right, on the next one, we have a few pieces. We're dealing with a cube root, for one, and we have a negative. Is this negative going to cause us problems in a cube root? Because let's think through our cubes for a second. If we did like 1 cubed to be 1 times 1 times 1, if I did 2 cubed, it's 2 times 2 times 2. What happens if I do negative 1 cubed? What do we get? Negative 1 times negative 1 times negative 1. We get a negative 1. If I do negative 2 cubed, we'd wind up with a negative 8. So we can have negative cubes. It's the even degrees, the even powers, that we cannot have negative. That's when we get I. If we have a negative number and an odd power, we're totally fine. That's doable. So when we split this up, you can choose to either split this up like we did for I, where we have our negative 1 and our 27 separate. But since it's an odd number here as our index, we can keep them together. So we're going to have our cube root of negative 27, our cube root of x to the 6th, and our cube root of y to the 14th. So when we come through to try and simplify our cube root of negative 27, what are we going to get? Yeah, it's going to be a negative 3. So if I continue doing this up here and I went through my negative 3 cubed, we would get a negative 27. So the cube root of negative 27 is just negative 3. And that's when you can put in the calculator. And y'all need to turn the headphones down. Oh, it's time for me to do some bad dad dancing. I'll play upon the headphones and badly dance to your music. I will kill a song. I've been known to do it. Turn your music down or I'll kill the song. There we go. Yeah, that's the volume your headphones should be at. That one right there, right there. If I can hear it loud enough to dance to, so can everyone else. Really tired of having that conversation in here. Really tired of it. Oh my gosh. All right. So let's do our next piece up here. Our cube root of x to the 6th. What do we get on this guy? X squared. I have 6 things. I can make groups of 3, and I can make 2 groups of 3. How about for my cube root of y to the 14th? Yes. So we're making our groups of 3. I can make 4 groups of 3. That would get me up to using 12 of my y's. So if it helps, for some of us it'll help to write it like this, where I have my y to the 12th, because that's something I can make a group of 3 out of, and a y squared, just so we can keep track. You don't have to write that step down, but for some of us, that'll be really helpful, because our leftover bit is that y squared. The only chunk I have left inside my radical is that y squared. And since the 2 is, in fact, smaller than our index of 3, we're done. That's how we can tell we're done. If the powers inside are smaller than our index, that's when we stop. So this is our fully simplified answer here. Okay. Questions on that one? Or either of those ones? Yes, sir. Correct. Yeah, the y to the 4th comes out because that is our group, the number of groups of 3 I could make out of the 14. I can make 4 full sets. We're going to practice this more because I've had a lot of people getting stuck on this kind of stuff. Mm-hmm. That's how many we had left over after the 14. Mm-hmm. What's up? It's what we looked up at the top there with the cubes. When we have negative cubes, it's going to be whatever that value is. So 27 is the same thing as 3 cubed. So negative 3 cubed gives us negative 27. So when we have odd indexes, we're going to have we can have negative numbers. We don't get I. It's only with evens that we get I. The negatives don't show up super frequently, but occasionally they'll show up. PSAT loves to throw them in as wrenches. So we're going to continue practicing this, and I've given us a lot of space on this page because I ran out of space on the last one. It looked chaotic. So we're doing the cube root of 24 a to the 6th over 125. when we have fractions, you can absolutely simplify inside first if it's able to do that. This one won't simplify in that way, but if you could, you could. So what we're going to do is we're going to use both the quotient property and the product property to split up this cube root and make this be something that's way easier to work with. Because we're going to do our cube root of 24, our cube root of a to the 6th, and our cube root of 125. And then I'm going to simplify each of those pieces individually to then put it back together as a fraction. And I'm actually going to go in what feels like a very backwards order, but I promise I'm just saving the 20. I'm going to save the 24 for last. So let's do our cube root of 125 first, because I'm picking it. So what do we do for our cube root of 125? Yeah, that one does come out nicely. It goes in the calculator. You can absolutely do that. If you didn't want to do that, or you didn't have a calculator that would do that, I'm just going to talk us through it real quick so we see it. I could also break this up to be 5 times 25 and start kind of factoring it out. And then I could break the 25 down into being 5 times 5. So this is 5 times 5 times 5, right? And in here, now I have a set of 3. So this is what the calculator is doing for us. It's finding that set of 3 in there. So these guys get to come outside, and this becomes just 5. It's what the calculator is doing for us. And most of the time, we are perfectly happy to let the calculator do it for us. However, sometimes it doesn't come out all pretty like, and we got to do it by hand. So our cube root of 125 does equal 5. And you can absolutely type it in the calculator, but I promise I did that for a reason. So let's look at our 24 next. Our cube root of 24. If you type that in the calculator, it gives you a super gross decimal. It can't simplify cube roots the way it does square roots, so we've got to do it ourselves. So we're going to break 24 down into factors to see if we can find a group of 3 in there. So what's something that multiplies to make 24? 6, not 6 and 3. 6 and 4, yeah. 6 times 4 multiplies to make 24. I don't see a set of 3 in here, so let's keep going. Let's break them down even further. I'm going to stick with my 6 and 4. What multiplies to make 6? 3 and 2. What multiplies to make 4? 2 and 2. With our index of 3, we're looking for those groups of 3. Do I have a group of 3 in here? Do I have a set of 3 things? What do I have a set of 3 of? 2s. So these are my funky looking socks, if the socks help you. I need a group of 3 because that's my index. So the 2s get to come outside. But we have a leftover bit. I have a leftover cube root of 3 that does not get to come outside. So my cube root of 24 simplifies down to be 2 cube root of 3. And I know that simplifying these when they're gross and leave us with leftovers is annoying and weird and confusing. That's why we're practicing this today. We've got one more piece on this one. That's our cube root of a to the 6th. What does our cube root of a to the 6th simplify down to be? A squared. So we have our a squared here. I recommend we switch this around to have my a squared in front of the radical, but honestly, if you do this and you just make it really clear, I won't take points off, as long as I can tell your a squared's not in the fraction. But the best answer would be 2a squared cube root of 3 over 5. So this is good, this is better. But I would take both, as long as it's really clear that this guy is not in your square root. If your square root comes over to here, less good. So just be careful. So that's our answer. Questions on this one? Because we've not done a funky root that had a leftover before. Okay, let's practice a little bit more. Here we have a 4th root. So we have an index of 4, meaning we're going to be looking for groups of 4. So I'm going to start using those properties to split this up into our pieces that are easier to deal with. So we can do our 4th root of 80 and our 4th root of y to the 14 and our 4th root of 256 and our 4th root of z to the 4th. So there's a lot of pieces here. We're just going to take them one at a time and simplify each one individually to put them back together. So with our index of 4, we're looking for groups of 4. So when we look at our 4th root of 80, why I made that tail so long. What can I do? What's going to multiply to make 80 that we could split this up into? 8 and 10 is a fine place to start. 8 and 10. I don't see any groups of 4 yet, so we're going to keep going. So 4th root of, what multiplies to make 8? 4 times 2. And what multiplies to make 10? 5 times 2, or 2 times 5. I see a whole bunch of 2's in here. Let's break this 4 down, because we're looking at our 4th root. 4 I can write as 2 times 2 times 2 times 2 times 5. So this 2 is this 2, and this one is this one, just so we can tell where these are coming from. I switched the color coding a little bit. So do I have a set of 4 in here? Yeah, I have one set of 4 2's. So our simplified radical form, the 2's get to come outside because they have their whole group. And we have our leftover bit that gets to stay inside the radical of that 5. He does not get to come outside. So our 4th root of 80 is the same thing as 2 times the 4th root of 5. So that's one piece of my thing up here. 2 4th root of 5. Then let's look at our next piece, our fourth root of y to the 14. I'm just going to draw a little barrier here so we can keep things organized. Fourth root of y to the 14. We're looking for groups of 4. So how many groups of 4 can we make? We can make 3 whole groups. I'm going to write an in-between step. You do not have to write this step, but for some of us it's going to help. So for our groups of 4, I could make it be y to the 12th times y squared, because I can make groups of 4 out of this one evenly, and this is going to be my leftovers. So we have 3 whole groups and our leftover bit of y squared. My power inside is smaller than my index, so we're good to go. So my simplified version of the y to the 14th is my y cubed, fourth root of y squared. There we go. Just giving us a little bit of space. All right. The denominator is actually easier than the numerator was. Because 256 is in fact a perfect fourth. You can type it in the calculator and it gives you a whole number. You're always welcome to test that and check that first. Or you can realize that 256 is 4 times 64, which is 4 times 16, which is 4 times 4. So this is going to be a 4. I'll write it out real quick. A fourth root of 256. Again, you can type that in your calculator, or you can break this down the same way, where we have 4 times 64, which is the same thing as 4 times 4 times 16, which is the same thing as 4 times 4 times 4 times 4. And there's way too many dang on 4s, but it just simplifies down to be 4. So you can do it by hand, or you can use the calculator. If the calculator gives you a whole number, you're good. If it does not give you a whole number, then you've got to do it by hand. Because the calculators are good, but they are not perfect. Our last piece up here, our green piece, our fourth root of z to the 4th is just a z. I have 4 things. I'm making groups of 4. So this simplifies down to be just z. So I was blocking that off. That was our little workspace. Because now I'm going to rearrange this, because we have one more step we need to do on here. We need to check and see if we can simplify our fraction, and that's easier to see if we have it organized nicely. So all my things that are outside the radical go together. So I'm going to have my 2y cubed, fourth root of 5y squared over 4z. Does anyone see anything we could simplify here? Like a normal fraction, old school fraction simplifying. Yeah, the 2 and the 4 are both divisible by 2. So we can simplify this. 2 divided by 2 gives me 1. 4 divided by 2 gives me 2. So this does in fact simplify. If it can simplify, I do need you to simplify. This is our last step. So our y cubed, fourth root of 5y squared. There we go. Over 2z. So if we can simplify our numbers or our letters, I do recommend you do that. You can also, if we could simplify here, a lot of times we could simplify here. 80 over 256, that does simplify down. But it's okay. We can also simplify it at the end. It would have given us a 5 over 16. So these have a lot of pieces, and we really just need to take our time and be super careful with it. Questions on this one? Okay. So I know I gave you guys a new homework yesterday, and this is really closely related to what we did Monday and Tuesday. So I'll wait and give you the next homework till tomorrow, because most of what we're doing is tomorrow anyway on homework 3. So that means we'll have a homework tomorrow and a homework Monday, and that is the end of homeworks. After that, it's just reviews. Okay? So we have 5 minutes left. So if you have homework questions, now's a great time to do that. If you got things to work on, now's a great time for that. Blah, 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 blah. Okay? So do the thing. Rock on.